In this video, I'm going to go through OCR AS-level Chemistry. This is paper 2, and this is the 2019 paper. Okay. Right, and this is the second half of the paper. I did the first half in an earlier video. Right, zinc reacts with hydrochloric acid as shown in the following equation. The student investigates the rate of reaction. The student plans to react HCl 50 centimeters cubed, 0.1 mole per decimeter cubed, with 0.2 grams of zinc, which is in excess. Calculate the volume of hydrogen that should be produced at RTP. Okay, so the zinc is in excess, so we need to work out, not all of the zinc is going to react. We need to work out the moles of hydrochloric acid. And from that, we know that 2 moles of hydrochloric acid is going to give us 1 mole of hydrogen. So moles of HCl, first of all, is equal to the concentration multiplied by the volume in dm cubed. The concentration is 0.1. The volume is 50 divided by 1,000. 50 centimeters cubed divided by 1,000 to get it to dm cubed. That gives us 0.005 moles of HCl. Now we said it's a 2-to-1 ratio, so we can say from that, so the moles of H2 produced is going to be 0.005 divided by 2, which is 0.0025 moles of hydrogen gas. Now we calculate the volume that should be produced at RTP. Well, the volume of 1 mole at RTP has a volume of 24,000 centimeters cubed. So the volume of gas that we're going to produce is equal to the moles multiplied by 24,000, which is of course 0.025 moles. We just worked out before. 0.025. That gives us a volume of 60 centimeters cubed. Okay. Right. Now, so that's how much gas we expect to be produced when the reaction is finished. Okay, this is the student's method then. So he's going to puts the HCl into the conical flask with the zinc, and quickly put the bung in and collect it in the gas syringe. And he measures the volume every 20 seconds. Right, so here's the results, and we've got to plot them, first question, on the graph paper. Then we've got to circle any anomalous results and draw a best fit smooth curve. Right, now the y-axis has been labeled for us, centimeters cubed, and you have to choose a suitable scale for the x-axis time. So it's 200 seconds there. Let's draw a line of best fit there. I would draw something like this. Go through the origin, of course, at time 0 there's no, so this one, the 80 seconds reading seems to be off the line. That's the anomalous result, and so that's our 2 marks there. 1 mark for circling the anomalous result, 1 mark for drawing the line of best fit. Okay, right, I'm going to do this question here now. All right, the student repeats the experiment using zinc with the same mass and the same surface area, so that's the same, and the same temperature and pressure, but they've changed the concentration of HCl. They've changed it to that and the volume. Before they used that volume and that concentration. Now we need to, obviously this one, the green one, the new one, this is going to be faster, so we need a steeper curve. It's going to be faster because the concentration of the acid is a bit higher, 0.125 instead of 1 for the other one. But we need to work out where does it level off. We need to work out the moles of HCl. So in the first one, the moles of HCl we just worked out was 0.005. Let's do in the second experiment, how many moles of HCl do we get? Moles is equal to conc times volume. We've got 0.1 multiplied by 50 over 1,000. course, that's the same because you've got the same moles of HCl. So well, that means we are going to get the same volume of hydrogen gas produced. So it's going to level out at the same point. So the two things we need to do, we need our curve to be steeper because the reaction is faster, but we want it to level out at the same point. So it will be 2 marks, and one for the that's steeper. It's going to level out at the same point because you're going to produce the same volume of gas because you've got the same moles of HCl in each case. So that would be, that's the line you want to draw there. Okay. Right, the graph shows the rate of reaction decreases over time. Explain why in terms of collision theory. Right, so what we're going to say, right, I would say, right, first of all, the concentration of the acid will fall. H plus ions, let's say, as time goes on because they're being used up. So they're less likely to collide with the zinc solid. Okay, and I think that's going to give you 1 mark. And I think you also need to say that during the course of this reaction, the zinc is going to react. So the pieces of zinc get smaller because they're getting used up. So that means the total surface area will also decrease. So that means collisions are less likely because you've got less surface area. So I think you need to make both of those points about the concentration of the acid and the fact that the zinc is disappearing as well. Okay. Right, the rate of the reaction between zinc and hydrochloric acid can be increased using a copper 2 sulfate catalyst. Okay. How does a catalyst increase the rate of reaction? Standard question for 2 marks. You need to say provides an alternative route, 1 mark for that. Second mark with a lower activation energy. That's a standard question. Right, now the next question. Why is it difficult to classify the solution of copper? It's a solution of copper 2 sulfate as a homogeneous or a heterogeneous catalyst. Well, let's think about what phase is the copper sulfate in. Well, it's aqueous solution. See, aqueous. Let's look at the zinc. The zinc reacting, zinc is a solid, and the hydrochloric acid is in aqueous solution. So you can't say it's homogeneous. Well, you could say it was homogeneous because it's in aqueous solution, like the hydrochloric acid, or you could say it's not homogeneous, it's heterogeneous because it is a solution and you've got zinc, which is of course a solid in a different phase. So that's all they're asking you there, 1 mark. Right, organic chemistry. Question 5, about hexene, and it's reacted with H2, HCl, and Br2. Complete the flow chart to show the structures of the products. Now, if you react it with H2, you are going to, let's draw hexene first of all. You're going to have 2, 3, 4, 6 there. You're going to have the double bond there. Okay, I won't bother drawing in all the hydrogens. Right, if you react it with H2, you're going to get an addition reaction. So you add the hydrogens across the double bond. So you're going to get hexane. That's pretty straightforward. The next question is a bit, this one is a bit hard. We've got to draw the major product, okay, when you react it with HCl. So when you react it with HCl, you could have the hydrogen, first of all, could stick onto that carbon. Okay, now I'm going to draw this out a little bit, I think. Let's see why is the just, are we? Right, so I'm going to just write, right, it could, the hydrogen could, well, you could end up with the hydrogen could stick onto the first, onto that carbon. That means you would have the bromine, well, you'd have a carbocation there, and that would of course be a primary carbocation. Alternatively, the hydrogen could stick on the other carbon. I draw this here, the blue one, so you could end up with the hydrogen sticking on the end carbon, and that would give you a secondary carbocation, and that would give you the 2-bromo. The bromine would then stick on that carbon. In the case on the top there, I'll draw it in black. You'd get it the other way around. The bromine would be on carbon atom number 1. So they're the two possible products. We've got to say which one is the major product. Well, the major product will be this one. Why is it a major product? Because it occurs through this carbocation, which is a secondary carbocation, which is more stable than the primary carbocation. So you're going to get 2-bromohexane as the major product. So if I just draw that there. The bromine is on carbon atom number 2, not on number 1. That will be the minor product. You get a bit of that, but not as much. Right, and then what would it look like if it reacted with bromine? Well, that is fairly straightforward. You would just get a bromine sticking onto that carbon and a bromine sticking onto that carbon. If you react with Br2, so you'd have 1,2-dibromo would be the product there. Drawn too many carbons there, I think, haven't I? Get rid of one of them. Okay, so that is the product there. Right, now the next question, fairly straightforward. What's the catalyst needed in reaction 1? Well, you know it's a nickel catalyst, isn't it? And what would you, question 2, it says, what would you observe in reaction 3? What would you see here? Well, bromine water is red, and so it would decolorize the bromine, or if it's added in bromine water or bromine, doesn't matter. It will decolorize the bromine. So you lose the red color. Okay. Right, now here is a reaction. It's a dehydration reaction. So we are going to lose the OH, and we're going to lose a hydrogen from the carbon next door, and we're going to end up with a double bond there to form that. Okay. So hexene, it gives us its boiling point and it gives us its density. We're going to need that later. You prepare hex 1 in this by refluxing with an acid catalyst. Okay. Notice hexene 1-ol has got a much higher boiling point than the hexene, and that's because you can form hydrogen bonds in hexene 1-ol, and you're only going to get London forces in hex 1-ene, which are of course weaker. Right. After the reflux, the mixture contains unreacted hexene 1-ol, hex 1-ene, and the water, and also the acid, and the mixture can be purified. Right, now the expected percentage yield, it's just a calculation, this first bit, is 62.5%. A student wants to make 4.2 grams of hex 1-ene by this method. Calculate the mass of hexene 1-ol he should use. Okay, let's do the calculation bit first. Okay, so what we're going to say there is we need to the MRs of these things. This would be useful because the MR of hexene 1-ol is going to be 102, and it's C6H14O. And a quick way of doing this, well, this is going to be 18 lighter because it's lost a water molecule for hex 1-ene, so the MR of that is 84. 102 minus 18 is 84. Right. So he wants to make 4.2 grams of hex 1-ene. We need to work out how many moles of hex 1-ene that is. And we know that 1 mole of hexanol gives us 1 mole of hex 1-ene. So we can find the moles of hexanol we need. So let's do the moles of hex 1-ene first of all. Moles hex 1-ene is equal to mass over MR. The mass we need is 4.2 grams divided by 84. That gives us 0.05 moles. Right. Now, so the moles of hexanol we would need, if it was 100% yield, would be the same. So I'm going to write that down. So if 100% yield, moles hexane 1-ol needed is equal to 0.05. We don't get 100%, you only get a 62% yield. Now I'm going to pretend we only get a 1% yield. So if we get a 1% yield, right, the moles of hexane 1-ol we're going to need there, we're going to need 100 times that, aren't we? So we're going to need 0.05 times 100, which is equal to 5 grams, 5 moles, sorry. But we don't get 1% yield, we get a 62.5% yield. So how much are we going to need there? We're going to need 5 moles divided by 62.5, which gives us 0.08 moles of hexane 1-ol. That's what we need. So what is the mass of hexane 1-ol we need then? Is equal to moles times by the MR. So that's going to be 0.08 multiplied by the MR we said was 102, which gives us 8.16 grams. And that's what it asks us to work out the mass of hexane 1-ol. We'll need 8.16 grams for that. Right, now the next bit of this question, how are we going to explain how you could obtain pure hex 1-ene from the mixture obtained after reflux? Right, now what we're going to say, hexane 1-ol is soluble in water because it's got an OH group, which means it can form H bonds with the water molecule, so it will be soluble. Whereas hexene cannot form H bonds, it's going to be insoluble, immiscible, with water. So if you mix water with hex 1-ene, you're going to get 2 layers. Okay, so what you should do is you should get your, this is your, you're going to get your hex 1-ol mixture, hex 1-ene, hex 1-ol mixture. So that is, I'll draw them like that. So you've got your hex 1-ol and you've got your hex 1-ene mixture in there. And you're going to add to that some water, and then you're going to, what will happen is this will dissolve in the water, but this one will not dissolve in the water, and then you're going to separate them using the separating funnel. So this is a separating funnel. They come in various different shapes and sizes, but there's my separating funnel. And the important thing is got a tap on the end of it. You're going to put that mixture into there with some water, and you'll end up getting 2 layers. Now the density, it tells us the hex 1-ene is less dense, so this is going to be your hex 1-ene layer, the bottom one. Sorry, that's not going to be the hex 1-ene is less dense, I beg your pardon. So that's going to be the top. That's going to be hex 1-ene on the top there, and this is going to be your hexanol and water. Okay, and you give it a good shake to make sure all the hexanol is dissolved in the water, and then you drain away and throw away the hexanol layer, and you keep your hexene layer. And then what you should do is you should then finally, you should distill, you do fractional distillation of the hex 1-ene, tells us its boiling point was 87 or something, or 63 degrees C, sorry. Okay, so you should collect the fraction at 63 degrees C. So use a separating funnel, shake it with water, and then distill. Important there to realize that this is going to form H bonds and will be miscible with water, and this one will not, and it won't mix with water. Right. Right. A student suggested hex 1-ene could be prepared from hexene 2-ol. Would you expect the percentage yield to be greater, less, or more, whatever? Okay. Now let's have a look at that. Now, if you've got hex 2-ene, hexene 2-ol, sorry. Right. So there's hexene 2-ol. You've got an OH there. Now, to dehydrate it, you are going to remove, we'll draw all the hydrogens in, you remove the OH and you remove the hydrogen from the carbon next door. Now this has got 2 carbon next door, so if it removes, let's say, that blue one, you're going to end up with the double bond forming there. You're going to get hex 2-ene, right? Whereas if you move the red one, you get the double bond there. If you move that one, you get hex 1-ene, and so you are definitely going to get a lower yield with hexene 2-ol, because you can form 2 different products possible. So you're certainly going to get probably only half as much, whereas with hexene 1-ol, there's only one possible product, which is of course hex 1-ene. Okay, so that is the answer to that question. Okay, hex 1-ene can be polymerized to form polyhex 1-ene. That's okay. So now it's important when we draw this. So when we do polymerization, if you think ethene, how does that polymerize? Well, you get your ethenes. So let's draw 2 next to each other. It's asked for 2 repeating units. So now all that happens in ethene is you break the double bond and you form a new bond between the carbons, and you break these. Yeah. Right, now this is exactly the same thing is going to happen with hex 1-ene, but we just have to remember here that in hex 1-ene, that's not a hydrogen there. That is C4H. It's a butyl group. Okay, so that's an H9, that will be, won't it? So 4 carbons with 9 hydrogens attached to it. So you're going to get that there, and you're going to get that there as well, C4H9. So when you polymerize that, we're going to form a new bond there, and we're going to get rid of these ones. And I'll draw this carrying on there. We've got 2 repeating units in that. Okay, we've got, just to show you, we've got that bit, that's 1 repeating unit, and that's the next one along. Okay, you don't need those green brackets, just need to draw that. Okay, right, waste polyhex 1-ene can be disposed of usefully by recycling. State 2 other methods of disposing of polymers that can be beneficial to the environment. Right, well, you can burn them to use them essentially as a fuel, to heat things up or to generate electricity or whatever. So you're using it as a fuel. That's one way. That's good because it saves you using other fuels. The second one, well, landfill, that's not going to be beneficial to the environment at all. What could be beneficial is that you could use them as a starting material for organic synthesis. Sometimes called like a feedstock. Okay, so make other organic molecules out of them that are useful. Right, I think that is the end of the paper.